What really sits between a sender and a receiver? Not a perfect wire, a channel that can scramble symbols. A discrete memoryless channel is defined by three things: a finite input alphabet X, a finite output alphabet Y, and a transition matrix of conditional probabilities. Each entry, P of j given I, is the chance that output Yj shows up when input Xi was sent, and every row must sum to 1, something always comes out. Memoryless means each symbol is scrambled independently of the past. That matrix is the whole story of the noise. Once symbols cross that channel, how much information actually arrives? That is mutual information, also called transinformation. For one pair, Xi sent and Yj received, the mutual information is the log of how much more likely that input becomes after seeing the output. Averaging over every joint pair gives I of X, Y. After a short derivation with Bayes' rule, it collapses to a clean identity. I of X, Y equals H of X minus the conditional entropy H of X given Y. In plain words, source uncertainty minus the uncertainty that remains after you hear the output. That difference is what the channel truly carried. Mutual information has three equivalent faces. I of xy is h of x minus h of x given y. It is also h of y minus h of y given x, and it is h of x plus h of y minus the joint entropy. Picture a bar diagram. Joint entropy sits on top. The overlapping middle is shared information. The wings are the residual uncertainties. On an ideal channel, those residuals vanish, so I equals h of x equals h of y. On a fully scrambled channel, h of x given y equals h of x, and mutual information drops to 0. Noise ate everything. H of x given y is exactly the information lost due to noise. The form we use most is I equals h of y minus h of y given x, because it leads straight to capacity. The workhorse example is the binary symmetric channel. Inputs and outputs are just 0 and 1. With probability q equals 1 minus p, the bit arrives correctly. With probability p, it flips. That single number p is the crossover, or error probability of the modulation. The transition matrix is neat. 1 minus p on the diagonal, p on the off diagonal. Symmetric means 0 and 1 suffer the same flip rate. The channel has no favorite bit. Channel capacity is the largest mutual information the channel can ever carry, max over input distributions of I of x, y. For many discrete channels, that max simplifies to log 2 of n, the output alphabet size, minus the noise entropy h of y given x. For the binary symmetric channel, n is 2, so capacity is 1 minus that conditional entropy. Working through the joints, h of y given x collapses to the binary entropy of p, minus p log p minus q log q. So C equals 1 plus p log p plus q log q in bits per channel use. When p goes to 0, C goes to 1, a perfect bit. When p is 1/2, C is 0, pure noise, nothing gets through. And oddly, p equals 1 also gives C equals 1. A bit that always flips is still perfectly informative if you just invert it. Plot capacity against the flip probability, and you get a U-shaped curve, high near 0 and 1, dead at 1/2. Now connect P to the physical world. For BPSK and similar binary modulations, the bit error rate is 1/2 times ERFC of the square root of EB over N0. As signal to noise rises, P falls and capacity climbs toward 1 bit per use. At about 10 decibels of EB over N0, capacity is essentially 1, and the error rate drops below 10 to the minus 5. The math of the channel and the physics of the radio meet in that curve. Shannon's second theorem, the channel coding theorem, is the payoff. For any rate R strictly less than capacity C, there exist codes of that rate whose decoding error probability can be driven arbitrarily close to 0. Below capacity, reliable communication is possible. Above capacity, it is not. Shannon does not hand you the code. Finding practical constructions is the job of coding theory. It took about 45 years after 1948 before turbo codes finally approached that limit with manageable complexity. Capacity is not just a number, it is the hard ceiling on reliable rate. A different model is the binary erasure channel. Here, the bit is never flipped. It either arrives clean or it is erased, replaced by a special symbol epsilon. Probability of erasure is p. probability of correct delivery is 1 minus p. The transition matrix is 2 by 3. From each input, probability 1 minus p goes to the matching output, and p goes to erasure. Nothing crosses from 0 to 1 or 1 to 0. When you do receive a bit, you can trust it completely. That is why erasures are often easier to correct than flips. Finally, the continuous world, the additive white Gaussian noise channel. Capacity becomes C equals W log base 2 of 1 plus P over N in bits per second, bandwidth times log of 1 plus signal to noise ratio. Write noise power as N0 times W, and something subtle appears. As bandwidth goes to infinity, capacity does not. It saturates at P over N0 natural log 2. Infinite bandwidth is not infinite rate. Divide by W and you get spectral efficiency, eta, in bits per second per hertz. Rearranging with energy per bit yields the famous bound, EB over N0 must exceed 2 to the eta minus 1 over eta. That inequality is the ultimate trade-off between power and bandwidth for reliable communication. From discrete matrices to this continuous limit, that is the map of transmission channels.